Hello everyone, I hope you're all doing well. Welcome to our applied mechanics lesson yet again. So today we're starting a brand new chapter, brand new module, and essentially it will be all about how to determine two unknown forces in a system of coplanar concurrent forces. Since this is an introductory lesson, it will have quite a bit of background information and the video might actually be lengthy. So I've just put on a disclaimer on there. No one comments about, yo, this is so long. Oh my gosh, oh my gosh. I have to be thorough with it, okay? So for starters, I want us to familiarize ourselves with some symbols, some terminologies that we will be using throughout the system. So for starters, we have a symbol, sum of the perpendicular forces and components that takes the right as positive, okay? Then we have one that's almost similar to it, sum of our perpendicular forces and components that take the, well, upwards as positive. I don't know, get it there what, okay? So normally when we'll be calculating, you have to assume a direction right off the bat. And obviously, if you are busy calculating and the answer you get is negative, it then means you actual force is in the opposite direction that you assumed. It doesn't mean that your answer is wrong. It just means you assumed a direction that's opposite to the actual one that's happening, right? Then we have the term concurrent forces. So concurrent forces are forces that are meeting at a point. And on here, we are essentially talking about forces that are meeting at a specific point. Then when we are talking about coplanar forces, we're talking about forces that are acting on the same plane, okay? And this will make sense once we start going through our example. But if, for instance, we have this plane, we'll just say FF, and we have a force happening there, a force happening there, a force happening there, and we also have a plane GG on there, and we have a force happening here, force happening there. Hey, there's just a lot going on. So coplanar forces are essentially forces that are happening in the same plane, which is essentially how we'll go about dealing with this specific module. All right, so we are gonna go through essentially steps of how we're gonna go through solving it, and it looks difficult right off the bat, but I promise it's doable. Okay, so for starters, you need to assume a line of action of one of the unknown forces, because the questions that you'll be given will normally have two, sometimes more unknowns, but hopefully we're only dealing with two. You'll get two unknowns, and what you do, you start by assuming that one of those unknown forces is an actual plane. You use that as your baseline, and then you'll assume a direction, whether the other unknown is pushing or pulling, and then from that point you'll be dealing with an unknown, and then you will equate the algebraic sum of the forces or the components that will be acting perpendicularly to your assumed baseline, okay? And then you equate them to zero. That way you're able to solve for the unknown, and if you get positive, you get a positive answer, it means that your assumption was correct. If you get a negative answer, it means that your assumed direction is opposite to the actual one. Okay, so next we'll essentially be going into an example, and I hope I don't lose anyone at this point. Please bear with me. All right, so here we have concurrent forces that are acting in one plane and it is in equilibrium. Then the question will normally ask you to calculate the magnitude and direction of maybe A and B, or B and C, or whatever forces that you're dealing with. But on here we're dealing with forces F and R. Okay, so it looks something like this. This is what the diagram looks like. So we have F over there, we have R over there. They are unknown, so they don't have a specific direction. Then we have a force of 2 kilonewtons over here. Okay, then there's a dotted line on there that essentially helps us to come up with a direction or whatever. Then we know that the included angle on there is 150. Okay, then we know that the angle on here is 45. Then we know that the angle on here is 30 degrees. I'm just trying to decipher if this 30 was a value I calculated or a value that was given. But anyway, let's just do it step by step. Okay, so step one, we assume a single baseline. From what we see, we have two possible baselines on here. So baseline the first one could be R on there. Essentially, you'd be using R as your baseline. And the second one, you would essentially be using F as your baseline. When you choose a specific baseline, then it means the other one would be the only unknown, because you cannot get a component on the point that essentially is your baseline. All right, so step one, we're going to assume that F is our baseline. So like I said, I'm just going to recreate this. Step one, we're trying to come up with our baseline. So we have our FF on here. FF, okay. And then there was this line over here. Maybe let me use it in a different direction. Different color, sorry. Okay, then we had this force over here. It was 2 kilonewtons, right? And then we had R that was somewhere here. Okay, then we can assume that R is pulling away. If we get our answer as negative, then it just means it's pushing, it's not pulling away, right? And what we knew is that we had an angle of 150 degrees on there. Okay, and there was essentially the line extended from our 2 kilonewton force. We knew that that was a 45 and that was a 30. Okay, and then from that point on, excuse me, from that point on, we can essentially use the information that we have to try and calculate the information that we don't have. So we know that the angles of an entire revolution should give you 360, right? So you can add 150 plus 30 plus 45 plus the unknown. It should give you 360. So all of this gives me, it's a 225. 150 plus 30 plus 45. Okay, I get 225 degrees plus theta is equals to 360. Theta is 360 minus 225. And it gives me 135. Okay, so we know that the angle on here is 135. Okay, then from that point, we essentially we're moving one step closer to the answer that we are looking for. All right, we still don't quite have it, but we're there. We're moving. Bear with me. Okay, then step two, now we have our baseline. Step two, we are now trying to come up with forces that will be perpendicular to this baseline FF that we have come up with, because that is what will essentially help us to get the values. All right, we are trying to come up with the forces. Okay, so from this, before we move on to step two, now that we know we have an angle of 135 on here, using our baseline FF, we're trying to see what the angle on here is, but we already know the sum of the angles within a straight line is 180. So you can do 180 minus 135, and it tells us this is 45 degrees. Okay, this will help us in some way, shape, or form, because remember, if we're using FF as our baseline, it means we will need to represent this 2 kilonewtons in terms of our components, right? Then next up, we're moving on. We're trying to come up with those components. Okay, so normally for some people that can't quite imagine something when it's skew or slanted, I mean, I can easily flip my screen around, but when you're writing, you know, sometimes the direction tends to escape. Okay, so we're just going to use the same one. I've flipped my screen a little bit just so I can see some of these directions. Okay, so when we're using our baseline FF, right, the forces that are acting on it will be this 2 kilonewtons as well as this force at R. We've assumed that R is pulling away, and 2 kilonewtons already from the given question was pulling away, what it was already giving, right? Now we're trying to essentially come up with the perpendicular components for these lines. So it means the line has to be perpendicular to our baseline FF. So when we have FF, we need lines that will essentially be meeting FF at a 90-degree angle. That's what we mean by perpendicular components. All right, then looking at our diagram, right, Our R was at an angle. Wait. We didn't sort out the angle. Right. So on here, remember we said this one is 45 degrees. But then what does that leave us here? So 150 minus 45, because it's still that same 150. This gives us 105 degrees. Okay. I'm just trying to make sure that we have all our duckies in a row. Right. So 105 degrees. Then okay, sharp, no problem. And what am I missing? I feel like my diagram is a bit dizzy because if that is 105, then it means it should be more to the other side. Okay, let's just redraw this to make it make sense. Okay, so if now using the angles that we have, we know this one is, okay, if we had an imaginary axis, it would be somewhere here, just so we know what perpendicular would look like. Then we know this one is at 45, so it can be at like the halfway point, and that's our 2 kilonewtons. Then the perpendicular component would essentially be meeting this F line at 90 degrees. And since the 2 kilonewton is pulling away, the perpendicular component can also pull away. Okay. And if we have our angle of 45 on here, this line is opposite. It already tells us this will essentially be the sine component. So this will be 2 sine 45. We only need the perpendicular ones. Don't pay attention to the cos ones for now. Don't pay attention to the parallel ones for now. Okay. Then we've represented the 2 kilonewton one. Then now we are looking at our line R. So we said our line R is 105 degrees from your positive F side. Okay. So if we had a 90, then we would put it somewhere here. That's your R. Okay. So if it's 105 from this side, then it will be 75 from this side. Okay, then it's probably easier or better to use that 75, right? Then you want the perpendicular component, and since we have assumed that our R is pulling away, our perpendicular component can also pull away. Okay, it just helps us in terms of knowing whether it's pushing or pulling, right? Then we have our angle 75 on here. Then we know this is opposite, then it takes on the sine. Okay, please make sure that you refresh with our components video if you don't quite recall how to go about it. But this will essentially be our R sine 75 degrees. Okay, is there anything else I'm missing? I hope there's nothing else I'm missing. All right, then now we are considering the forces that we have on there. Okay, now we have our diagram. We're happy with it. Then using your FF as baseline, then you're going to take the sum of the perpendicular component, or the sum of the perpendicular forces. Okay, so the algebraic sum of your perpendicular forces acting on F, then you can also assume the direction, right? Then you could say this way is positive. It's slanting a bit because you remember our diagram is not completely straight, right? It's not. So this is still the direction similar to that, perpendicular to your FF, okay? Then you need to say the algebraic sum will be equating it to 0, right? Then we look at the forces that are acting on it. Firstly, we have that R sine 75. It is moving in the direction that we've assumed, so we will consider it to be positive. Then we have the 2 sine 45. It's moving in the opposite direction, that's why it is negative. Then next you just play around with your maths. R sine 75 is equals to 2 sine 45. Okay, then divide both sides by sine 75, divide by sine 75. Then your R will be equals to 2 sine 45 divided by sine 75. Then I get 1.464 kilonewtons. And since my answer is positive, it says vele vele R is pulling in that direction. So the assumed direction is correct. If my answer was negative, then it would say this R, instead of pulling away, it's actually pushing into our baseline FF, right? So that is part one. We've now solved for one of the unknowns. We know the value of R. Then next up, you're essentially going to repeat the same steps, but you're going to change the position of your baseline. So I'll just have it on this side so we can compare. Remember, our RR was essentially going this way. I hope I'm not messing it up. Yeah, it was going like that. So we can have baseline RR on here. And then we had our F that was at an angle of 75 from RR. And then we had, okay, my F was looking hella dodgy. You're looking dodgy, mama. So we'll just say 75, that's our F. And then we have that line. I hope the angle is right. Let's see. So it was 105 from R. Definitely not. It just might be. It might be because this would be perpendicular. It just might be. Let's give it a chance. Let's give it a chance. So if it was 105 from the side, then it would have been. Was it 105? 150. This girl. 150. So it'll be 30 on the side. Okay. And that's essentially what we need to proceed on this side, right? So we have RR as our baseline. Then now we're representing the perpendicular components. We can assume that F is pulling away. We can assume, right? Then it means the perpendicular component will be pulling away as well. Since it's opposite 75, it will be the sine component. So this will be F sine 75. Then on this side, we can adopt one on this side. Already our 2 kilonewton is pulling away. This will be 2 sine of 30, right? Have we included all the forces? I believe so. Then next, we are essentially going to take the algebraic sum of the component forces at R, and we can assume a direction. We can assume that F will be pulling in that way, equate them to 0. Okay? Why do we have a ruler on here? Oh, on me, sorry. So F sine 75 minus 2 sine 30 is equals to 0. F sine 75 is equals to 2 sine of 30 divided by sine 75 divided by sine of 75. F is equals to 2 sine 30 over sine 75. Then I get 1.035 kilonewtons, and since it's positive, it means vele our F is pulling in that direction. Okay, and that's essentially how we go about solving for two unknowns using whatever method this is called. If you have any questions, you know what to do. I'll be more than happy to assist. Until then, adios.